My project is based on Module 4, sections Orbital and Periodic Table Trends. Elements are arranged by their atomic mass rather than their mass number in order to represent the properties that reoccur periodically. The S and P blocks are known for their main group elements. The D block are transition elements, and the F block are the inner transition elements. The F block should typically be between the 6th and 7th row. However, this would make the periodic table too wide, so they put their own section underneath the periodic table. There are 3 types of elements within the periodic table: metals, nonmetals, and metalloids. Metals are good conductors of heat and electricity. They are malleable and ductile, which means they are flexible without fracture, and they have moderate to high melting points. Nonmetals don't conduct heat or electricity. They are usually brittle solids and can be gases at room temperature. Metalloids consist of a combination between metallic and nonmetallic properties. Coulomb's law is an experimental law of physics that quantifies the amount of force between 2 stationary points. The electric force between charged bodies at rest is conventionally called electrostatic force or Coulomb force. We use the information to calculate the force of attraction between electrons and the nucleus. In order for Coulomb's law to be applied, we must look at the valence electrons and shielding. Valence electrons are electrons present on the outermost shell of the element. These electrons are known to be very ready to bond, and they are free-floating and do not comply with the octet rule. The electron charge present in a valence cloud is much lower than it would be if the electrons were on the element's orbital shell. A cloud of electrons between the valence electrons in the nucleus do not feel as strong of a nuclear charge as the core electrons would on the orbital's innermost shell of an electron. This is known as shielding and is used to reduce the nuclear charge felt by electrons, to make it more negative. The valence electrons within the same subshell only screen each other very slightly, and the electrons of the nuclear charge decreases depreciatively as quantum number increases. Different shielding between S and S orbitals are than there would be between S and P orbitals. Some key overall trends that are present within the periodic table that won't be discussed today are ionization energy and the atomic radius. The ionization energy increases as you go from left to right and from down to up. As the ionization energy increases in strength, you can imagine electrons being pulled closer into the nucleus. As for the atomic radius, this goes in the opposite direction as it increases going from the left to the right and down, up to down. However, these need to be applied to the main group elements. As ionization energy increases, the atomic radius will decrease. If the ionization energy increases, then the atomic radius will decrease. So that's an example of an interrelated property of electrons. Electron affinity. Electron affinity is the enthalpy change that occurs when a neutral atom gains an electron in order to form a negative ion, particularly in a gaseous state. Atoms prefer to have filled or at least half-filled shells, so the tendency of an atom to gain an electron to fulfill the octet rule also contributes to the definition of electron affinity. If delta H is less than 0, meaning the atom has a negative electron affinity, it makes it more likely to attract an electron. If delta H is negative, it means that the atom or molecule is releasing energy, indicating an exothermic reaction. However, if it is positive, the atom is absorbing an electron and is experiencing an endothermic reaction, and further electron affinity will not be possible. Within reactions, it is key to examine electron changes, orbital and electron configurations in order to determine the overall electron affinity, as well as the effect on electron-electron repulsion and electron nucleus attractions. Trends for electron affinity are shown in the diagram. 2 trends I'd like to point out are with group 1 and 2 and group 17. Group 1 and 2 atoms have difficulty attracting extra electrons because the extra electron would be added to a higher principal shell. In addition, the current electrons tend to shield the pre-existing electrons from incoming valence electrons. Within group 17 elements, they have the highest electron affinity because they want an extra electron to fulfill their outermost shell in order to apply and comply with the octet rule. Going down the periodic table for group 17 elements, it's seen that their electron affinity decreases because their orbital size is decreasing and the atomic radius as well is increasing, which expands and creates less attraction force for the electron to the nucleus of the atom. There are two types of electron affinity that can occur. The first is the electron affinity of an energy released when one molecule of the gaseous atom each acquire an electron to form one molecule of the gaseous, so one ion. It is shown using the example as well as the product will become an exothermic reaction and it will have more electrons than previous. The second is electron affinity, as it occurs when there is another electron being added towards the atom. So the second electron affinity is the energy required to add another electron to an ion and one molecule to the gaseous. So one molecule is produced of gas, which is resulting to ions being added to that molecule. Electron affinity is referred to trends going across groups and periods. Moving from left to right across a period, an additional electron is favored, and electron affinity becomes more negative. Additional electrons make the substance or mixture more exothermic due to the electron nuclear charge increasing as the trends are going from left to right across a given period. Groups experience the electron affinity is most negative at the top, and going downwards, the electron affinity becomes less negative because the incoming electrons are accommodating for larger orbitals and thus they are further away from the nucleus, feeling less of that electron to nucleus attraction. Typically, atoms in the second row have a lower and larger electron affinity than the third row because the atom orbital of the second row are much smaller. As well, incoming electrons encounter larger repulsion forces for another electron in the atom, and is not as tightly bounded as we might expect. So here are some sample questions. Which of the following atoms has the lowest electron affinity? And the answer is C. Radium is the farthest down the group of all the other atoms and will have the largest atomic radius. So it has the lowest electron affinity. Next, we have which of the following atoms has the greatest electron affinity? So take a moment. The answer is fluorine. It has the smallest atomic radius, and the answer is it is located furthest to the right of the period, as fluorine will have the largest attraction force between the nucleus and the electrons, having the highest electron affinity. So what is the main difference between atoms' electron negativity and its electron affinity? I'll give you a moment to read that. So the electron negativity and electron affinity can be easily confused. Both of these terms describe the resistance to gain an electron, but they do so in different classifications. Electron negativity describes how readily an atom will become an anion, or how easily it will accept an electron. The halogens have extremely high electron negativity, while the noble gases have virtually zero electron negativity. In contrast, electron affinity describes the energy change when an electron is added to an atom. The halogens, again, have a very high electron affinity, and the noble gases will sometimes have electron affinities that are negative, indicating that it's exothermic process to remove these extra electrons from the elements. So question 4, does electron affinity increase or decrease going down a group? So the electron affinity increases going up a group because of characteristics of atoms such as atomic size and radius. So arrange the following atoms in order of lowest to highest electron affinity. Well, the answer is C. The placement of these elements on the periodic table, as well as their radius size, contribute to the electron affinity in gaining an extra electron. Thank you for listening to this module overview, and I hope you enjoyed it. For additional practice, you can go to Chapter 9 of the textbook, and have a wonderful day, and I hope you learned something new.